Alright, today we want to calculate the head loss. In this question, we have two reservoirs. The first one, the water at the first one is higher compared to the second one, and the difference in the both reservoir height is shown by a component H. So, and they are connected through this pipe. The pipe initially has about 100 millimeter diameter, and then it will increase to about 200 millimeters. We know the mass flow is about 78.55 kilogram per second, and the pipe roughness is 0.2. In the first part, we want to identify individual head loss associated to all components. So it's important to identify all components. How are we going to do it? We started from here. The first one is the entrance, because we have a entrance, we will have a head loss in the system, and then we have a 45-degree bend, P1 and P2. The head loss through these two components are exactly the same. And then the third one, which is important, we have to consider, it's the sudden expansion. We call it, name it as a C. And the last one is the exit, which we call it D. They are the head loss, this component we identify related to the junction, exit, or entrance. We also have a head loss associated because of the friction in the pipe. So in this pipe, the diameter and velocity remain constant. The head loss associated with this pipe we show it with the 1, and the second pipe, because the diameter change and the velocity will change, we show it with second. So for the minor or for the junction, the formulation is HL is equal K V squared divided by 2G. So what we need to do to find the K for each component, either is the entrance, connection, or exit. The other component we need to find is the velocity. How are we going to find the velocity? We have the mass flow rate, and we know the flow is the water, so it means we can easily find the velocity. So if I'm using the mass flow rate, the mass flow rate is equal density times volume times area. We want to find the velocity in the first pipe, we call it with the V1. So if I just replace this parameter, (1000) times V1 times A1, and A1 is the pi times 5 squared. The diameter is about 100 millimeters, so it means the radius is about 50 millimeters, and we need to represent everything in the metric system. And we can find the V1, which is about 10 meters per second. Now we are able to calculate HL for the A, B, and also C. Just keep it in your mind, in this formulation, depends on which part of the system we are, we need to either use V1 or V2. So let's start with the HL1A. So the K factor will be 0.5. This is the type of the entrance is important, and we're going to use the table in the textbook. So this table provided all of them. So this is the page 316 from Potter textbooks, and we have 3 values for the entrance. But it's important to look at the type of entrance. The entrance here is the square H entrance, so the K factor will be about 0.5. So if you replace this value, 0.5, times v square, we just found it, divided by 2, and the gravity is 9.81, so it means HL will be about 2.458 meter. Just keep it in your mind, it should be at least 4 significant. For the second one, which is related to the elbow, we have a 45 elbow. Both they have the same amount of the head loss. And again, that's the same formulation, but the K factor will be different. We need to find the K factor. We call it K elbow times V1 squared divided by 2G. So it will be about, and again, if you look at this table, you have for the type of fitting, you'll have values depending on the diameter. So if you look at the table, the HL factor for the K factor for the elbow is about 0.29. 10 squared 9.81, and the value will be about 1.478. The unit is the meter. Just keep it in your mind, we have 2 elbows. At the end, we need to consider both of them. And the third one is the HL for the C. We need to look at the K for sudden expansion. V1 squared divided by 2G. The K for the sudden expansion, again, we need to look at this table. For the sudden enlargement or expansion, what we have, the K is equal 1 minus A1 divided by A2 squared. So the diameter for the first pipe is 1 squared divided by diameter for the second one, which is the pi divided by 4 times 0.2 squared. And total should be squared. If we replace these values, it will give us the K factor, which is about 0.5625. If we just replace it here, then we will have the head loss to this junction. Again, we're using it still V1 because that's the velocity is important for us. It will be about 2.867 meter. And the last one is for the exit. We also if you look at the K out, we need to also find the head loss at point D, which is the exit. But just keeping in your mind, we now need the velocity at point 2. How we can find the velocity at point 2? The mass flow rate in pipe 1 and pipe 2 remain constant. So we can write it, mass flow rate is the rho V2A2. So it means V2 is equal mass flow rate divided by density divided by the area. And if we just replace these values and the area, we can find the second velocity. And the velocity will be about 2.5 meter per second. Now HL for the D, it will be K out or exit V2 square divided by 2G. Again, from the same table, the K out is 1, V square 2.5 squared divided by 2 times 9.81, and the value will be about 0.386 meters. So if you compare them, you can see the highest head loss due to this junction, or we call them minor head loss, is associated to point C, section C, when we have a sudden enlargement. And the next large one is associated to the entrance, because we have a square shape, square edge, the head loss is quite large, the K factor is about 0.5. And for at the exit is not very large. The reason it's not very large, even the K factor is quite large, because the velocity is smaller, alright? Okay, now we have computed all the head loss associated to the junction. We need to find the head loss due to the, the friction in first pipe and second pipe. So the formulation for head loss in pipe is actually equal just make them separate. Maybe I can write it in the middle. So it's the F times L divided by D times V squared over 2G if the flow is turbulence. So the first step is to calculate the Reynolds number to tell us if the flow is turbulence or not. With the Reynolds number, we can then figure out which formulation we have used. If it's a turbulence, that's the formulation. And again, we need the Reynolds number to calculate the F factor. So if I write down the Reynolds formulation, it's the VL divided by mu. So Reynolds number for the first pipe will be the velocity is 10, the reference diameter is 0.1 or 100 millimeter, and nu or viscosity, kinematic viscosity is 0.00 times 10 minus 6. That's the viscosity for the water, and it gives us the Reynolds number is about 9.932 times 10.5, which tell us the flow is turbulence because it's higher than the critical Reynolds number in the rough pipe, which is about, it's much higher than the critical Reynolds number. That's the reason the flow is turbulence. All right. Now we have the Reynolds number, we know the flow is turbulent, so that's the right formulation, but we still need to find the F factor. How are we going to find the F factor? We need to use the Moody diagram. For the Moody diagram, we need two components. The Reynolds number, which already mentioned it, and also the roughness. The roughness is given is about 0.2 millimeters. We need to calculate the relative roughness, which is the ratio between the roughness and the diameter. For the pipe 1, it will be about 0.2 10 minus 3 divided by 0.1, which give us the roughness 0.2. If you look at the Moody diagram, just remind you what was the Moody diagram. So for the Moody diagram, we have a diagram at the right side of the diagram. There's a relative roughness, at the bottom is the Reynolds number. So with these two information, we need to project it to the left side of the graph, which is the F factor. So if I look at these values, it will give us the F factor about 0.024. And we can do the same for the second pipe. The second pipe, okay, before we move into the second pipe, maybe it's easier if I insert this parameter to the formula. So if I insert all of them, the HL for the first pipe will be equal F.24 times the length. So as I said, since the velocity and diameter remain constant from here to here, we can calculate or consider, the length of the total pipe. All right. So it means 10 diameter here, 10 diameter here times the sine divided by sine 45, and then plus 10 diameters. So